Hello, everyone. Can everyone hear me? Folks online? All right, excellent. All right, let's get started. As Beth said, my name is Jacob Lustig-Yaeger. I'm a staff scientist at Johns Hopkins Applied Physics Lab, and it is an absolute honor and privilege to be here. Thank you to the organizers for having me to speak about the amazingly rich field of exoplanet atmospheric studies. There's so much to say, so much amazing science, and so let's jump right in. Um, at its most sort of fundamental level and the most abstract way to say it, atmospheres are the interface between a planet and the rest of the universe. Simply put, they are a layer of bound gas that filters starlight incident upon the planet and moderates the light that leave it. They constantly undergo a dance of physics and chemistry that drive dynamics and climate. They are remotely observable through spectroscopy. Yeah, you want to move that? Thanks. And allow us to study them remotely. Whoops. Perfect. They are shaped to some degree or another by the formation of the planet and by the evolution of that planet over time. And planets like Earth and perhaps other planets out there can contain gaseous byproducts of life processes that effectively spectroscopically broadcast information about a global biosphere to the rest of the universe or to the nearby planetary systems where astronomers like us might be searching for signs of life. So in this talk, I'm going to cover in part one some basic principles underlying planetary atmospheres and their interactions with light. Then we'll talk about key levers that shape the observables of planetary atmospheres. And then in part three, I'll give a really brief overview of past and present results for direct imaging spectroscopy of exoplanet atmospheres and touch on some future goals. We'll be hearing a lot throughout this week about past, present, and future direct imaging results. So I hope to be able to highlight some of the future talks this week that will be fantastic and dive into more details. So let's just jump right into part one. At its most basic level, a planet's atmosphere must be stable against escape. This isn't too much of a concern for directly imaged planets, but when we think about thermal escape, we require that the escape velocity from the planet sufficiently exceeds the thermal velocity of the gas. So that sufficiently exceeds, we typically think about this rule of thumb, 6 times as long as the escape velocity is 6 times the thermal velocity of the gas, then we're stable against atmospheric escape. There are a bunch of different atmospheric escape mechanisms, and for particularly rocky planets, there are a host of different source processes like volcanism that can replenish atmospheres that have been lost over time. This hasn't been particularly relevant for really widely separated directly imaged planets, but is more relevant for the transiting planet community, and in the long run, we'll want to connect everything we've learned about transiting planets to the directly imaged planets with our future observations. So moving forward, planets that have atmospheres maintain hydrostatic equilibrium. And this is where the gravitational force downward or inward towards the planet is balanced against a gradient in gas pressure. And so if we combine this with the ideal gas law, we get the sort of simple intuitive understanding that the pressure of the atmosphere decreases exponentially radially away from the interior of the planet with this characteristic scale height h that describes the sort of extendedness of the atmosphere. So planets that have hotter atmospheres or lower surface gravities or are composed of gases that are low mean molecular weight tend to have more extended atmospheres that we can characterize with this pressure scale height. When it comes to modeling exoplanet atmospheres, there's sort of historically two broad camps of models where some folks have taken stellar models of how we understand stellar atmospheres and sort of scaled them down, while other researchers have taken richly detailed models from studying the Earth's atmosphere and kind of changed the context within which we're modeling those to understand different exoplanets that we may have detected but not yet have measurements of. So here for the stars down approach, we might start, we typically are talking about primary atmospheres composed of hydrogen and helium. We might start with the composition of the sun and then enhance the heavy metals or the metallicity of the atmosphere to get a substellar and a gas giant planet atmosphere compositions. And then we might tune certain knobs, things like the rotation rate to enter a different climate regime. We might change the type of star or the distance from the star so that we are getting different impacts on the atmosphere and the climate. And these models have worked really well for understanding stellar atmospheres, brown dwarf atmospheres, giant planets, ice giants, and into the mini Neptune super Earth's water world regime. They have been used, but there's still so many open questions about these types of atmospheres and planets where we don't have analogs in the solar system, that there's still a lot of open questions. On the Earth's up side of this diagram, we're typically thinking about smaller rocky planets composed of secondary outgassed atmospheres with heavier gases like CO2 and nitrogen. We might start here with like a template, start with Earth's atmosphere or Venus or Mars's CO2 dominated atmosphere, and then change things like the surface boundary conditions. What is the amount of, say, methane coming out of the planetary surface, or what's the surface pressure? So we can, and then we might change those same knobs that we do for the giant planet atmospheres to understand how and predict and interpret how the spectrum of an exoplanet might be observed. So this works really well for rocky exoplanets, whether they're cold, warm, or hot. And it still remains to be seen exactly what the nature of super Earths, these water worlds, ice giants are like. So regardless of the type of modeling, the radiative transfer equation in exoplanet atmospheres is critical. I'm not just showing the radiative transfer equation here with math because typically we're using numerical codes to solve the radiative transfer equation and keep track of the incoming solar radiation, how it's reflected and absorbed by the planet's atmosphere, how it heats the atmosphere, and how the outgoing long wave radiation is emitted to space. So we use the radiative transfer equation to understand how light enters and exits the atmosphere, how and where starlight heats the atmosphere and drives the climate, and how scattered light incident on the planet and emerging thermal emission escape to the atmosphere and become the observations that we can make. So sort of fundamentally, light and matter can interact in a handful of different ways. Light can be absorbed by some medium. It can be emitted by that medium or a gas, transmitted through, reflected off of. It can refract through it due to changes in index of refraction. And sort of at a common textbook picture of this for astronomers, we might have a continuous light source here that we can just observe. And we're just going to use this sort of weird physicsy diagram of an eye to think about what the observer would see if they observe this continuous light source, a cloud of gas, or the continuous source through the cloud of gas. And so if we just observe this sort of isolated star, we get a continuum spectrum, something here just depicted as a black body. If we just observe this cloud of gas on its own, we get an emission spectrum corresponding to the atomic molecular species in this gas cloud. And if we observe this continuous light source through the cloud of gas, well, then we get this continuous spectrum with absorption lines corresponding to the species in this cloud of gas and the temperature of the cloud of gas. So in a planetary atmosphere context, and in any context with spectroscopy, we take advantage of the fact that each atom and molecule have a unique spectral fingerprint. And as long as you have the resolution to observe those unique and distinguish those unique spectra. So on the left here, we're looking at images of gases heated in a lab, and we can see their individual emission spectra. And so for planetary atmospheres, we use this key tenet that the absorption and emission features pairs of molecules and atoms are sort of a universal. When we measure them in a lab here on Earth, we can use those to decipher the spectra of exoplanets and understand their atmospheres from light years away. So it's really fundamental that we make these laboratory measurements. They're so key to inputting into our radiative transfer codes and being able to interpret exoplanet atmospheres. All right. So that was a really high-level brief overview of the basics. And now we're going to jump into key levers that shape the observables of planetary atmospheres. So we're going to start here with the reflected and then the emission spectrum of Earth to sort of build intuition for a planet where we sort of intimately are aware of the sort of surface conditions and the temperature regimes. And then we'll take a step back and generalize some of the things to different planetary contexts, including giant planets. So we're going to deconstruct Earth's reflectance spectrum. Here we're looking at the geometric albedo of the planet as a function of wavelength. And I'm just plotting the spectrum as if light were just reflecting off of the surface and there were no atmosphere. And we see that there are bumps and wiggles in this, and that's because the surface albedo of the planet as a function of wavelength does encode information about the surface properties, the ocean, the land, the vegetation, that's all encoded in these bumps and wiggles. Now, if we add a nitrogen atmosphere on top of this, we see Rayleigh scattering significantly increases the reflectivity of the planet in the blue. And this is because Rayleigh scattering has a lambda to the -4th dependence. And so it's setting the continuum here at short wavelengths, but barely causing any additional reflectivity at the longer wavelengths. Now we can start to add in the gaseous absorbers that sort of absorb from that continuum. So we can start with oxygen, our sort of canonical classic biosignature. The ozone features and the optical and the UV are massive and are photochemically produced by oxygen. Carbon dioxide in Earth's atmosphere is a trace gas. It has subtle absorption features in the near infrared. Same with methane, a relatively trace gas, but is a biosignature as well. And then we add water in, and water has massive absorption features throughout this entire wavelength range. And when we put all these pieces together, we end up with kind of the full clear sky spectrum of the Earth along sort of cloud-free optical paths. So I want to now add clouds in to see how that affects things. So I'm going to change the y-axis a little bit here and to make some room for higher albedo cases. And I'll just make a note that with clouds, Rayleigh scattering plus the surface albedo is setting the continuum from which the molecules are seen in absorption. So this continuum is kind of backlighting the absorption features from the gases in the atmosphere. So now we're going to plot the continuum if we take a look at water clouds, stratocumulus clouds, and classic ice water clouds. These are kind of average clouds that we'd expect on Earth, and these spectra kind of represent if the planet were fully covered in these clouds. So one key thing is that they definitely increase the albedo of the planet. In this case, water clouds, as we all know, are incredibly reflective, but they also have absorption features that tell us something about the fact that these are water clouds. So we can actually uniquely identify clouds from absorption features. If we add the molecules back in, we see that some of the absorption features are significantly larger due to the fact that the continuum has raised up and we're getting just more light from the planet. But I want to highlight that, so this 1.6 micron CO2 features is very small if we don't have clouds, but is enhanced by the presence of clouds. So you can have enhancements of gases absorption features in reflected light under certain circumstances, but you can also have a decrease in the size of absorption features with clouds. Clouds are complicated, they make things hard, but in reflected light, sometimes they provide an opportunity to detect gases at higher significance, like ozone here is a larger absorption feature due to the clouds. But water is mostly blocked by these high altitude ice clouds because they're composed of the condensed species that we're trying to detect. And so they block access to the lower atmosphere where water is seen in vapor phase. All right, so in reality, Earth has about 50% clouds, 50% clear sky. So we kind of can get a weighted average of these to arrive at the sort of final Earth spectrum. All right. So we can play the same game with thermal emission. And in this case, we start with thermal emission from the surface set by the surface temperature of the planet. And from this continuum, we get absorption features from the cold layers of the atmosphere above. So we'll start with CO2, adding that in. There's this massive feature at 15 microns. We have ozone at 9.6 microns, methane, and then water sort of throughout this wavelength range. And so together, these gases sort of make up the clear sky thermal emission spectrum of Earth. And I want to take a second to dive deeper into the relationship between this spectrum and the temperature pressure profile of the Earth. And so here we're looking at the pressure decreasing, going up. So these are higher altitudes, and the surface is down here on the y-axis. And so this line corresponds to the continuum over here, where we get the hottest emission from the surface of the planet. And if we draw a black body at a temperature that skims the bottom of the CO2 band, the coldest regions of the temperature pressure profile of the lowest flux region of the spectrum are probing the tropopause here, where a lot of the absorption is coming from. If we take a look at an intermediate temperature that sort of skims the bottom of this ozone band, we see that it's coming from roughly the stratosphere. And that makes sense because ozone is concentrated in the stratosphere. So in this way, the emission spectrum is directly giving us a sense of the pressure temperature profile of the planet just by looking at the spectrum. We also see ozone or CO2 in emission at 15 microns because this ridiculously strong core of the 15 micron bands is so optically thick that the emission is coming from the hot stratosphere. And so in this way, we can sort of deconstruct a thermal emission spectrum and retrieve a temperature pressure profile from sufficiently precise measurements of planetary thermal emission. So we've only talked about clear skies so far, and so clouds come in here in a really interesting way as well. So if we plot the spectrum of our liquid water clouds here, we see that the continuum now has dropped significantly, and that corresponds roughly to emission around 274 Kelvin, which is 1 degree above freezing. So this makes sense for liquid water clouds, where now the emission continuum is coming from not the surface, but this sort of optical surface set by these optically thick clouds. So they're at altitude. They're not as high. They're not super high up, but they're water clouds. They're usually above the surface. And we can play the same game with cirrus clouds. So ice clouds are setting this emission from much higher altitudes where it's even colder. And so in this way, clouds can drastically affect the continuum emission from planetary atmospheres. And instead of the surface, are probing the cloud layers. And so that's really important for giant planets where there is no sort of physical solid surface, but instead there are numerous cloud layers, and we'll come back to that. So just like we did for reflected light, of course, Earth has partial clouds at any given time. And so the sort of final emission spectrum of Earth is a combination of clear and cloudy sight lines through the atmosphere. And day to day, moment to moment, as the cloud coverage changes, we expect this spectrum to sort of bounce up and down relating to the cloud coverage of the planet. And this can lead to planetary variability as a function of time, which is something we've seen with brown dwarfs and hope to see more of in the future with giant planets and even small planets. Okay, so that was our deep dive into Earth's spectrum to sort of build this intuition for how reflected light and thermal emission can allow us to probe composition in clouds, temperature pressure profile, and surface or optical surface conditions. So I'm going to take a hard left turn here and move to giant planets, where we often use metallicity to describe the atmospheric composition. And so metallicity is the factor by which metals, or any elements heavier than hydrogen and helium, are enhanced above their solar abundances. So here for instance, if we can calculate the metallicity by taking the number density of a species X. We can call it iron. It's pretty common to do the iron to hydrogen metallicity. And we divide it by the amount of hydrogen in the atmosphere, and then normalize it by that same ratio in the sun, and then take the log of it. So metallicity is really important because depending on the metallicity of a planet and the temperature and other ratios like the carbon to oxygen ratio, which is calculated in a similar way, these can dramatically change the expected equilibrium abundances of a planetary atmosphere and the emergent or reflected spectrum that we seek to observe. So in this figure, we're kind of looking at rows of different temperatures and columns of different metallicity enhancements. We're using the carbon to hydrogen ratio as a kind of a proxy for metallicity here, going from 10 to 100 to 1,000 to 10,000 times solar metallicity. When we transition from 100 to 1,000 times solar metallicity, that's kind of where we transition from being talking about a giant planet atmosphere to an atmosphere more dominated by higher mean molecular weight species like water. But one of the interesting effects is how temperature affects the expected composition here. So for taking a look at just 100 and 1,000 cases, we see at cooler temperatures like 500 Kelvin, methane is expected and is a great probe of metallicity in a planetary atmosphere. But at 1200 Kelvin, that methane is mostly gone, and instead we would be looking at carbon monoxide as a probe of metallicity here. So it really matters what temperature you're looking at. And so disequilibrium processes like photochemistry can cause significant departures from these expectations, but these have proved really useful for constraining the metallicity of giant planets and describing the atmospheric composition in a relatively simple way. To take a pretty simple look at how this affects the spectrum, here we can look at the reflected light spectrum of a hypothetical cloud-free Jupiter at like 1.2 AU from a sun-like star in reflected light. So here is a solar metallicity spectrum where these features are mostly dominated by methane and water, and this is kind of the corresponding pressure temperature profile that we expect for this atmosphere. If we also now plot 100 times solar metallicity enhanced spectrum, we see significantly more absorption throughout the optical. This is from about 100 times enhancement in methane and a factor of a few enhancement in water, leads to a dramatic change in the spectrum in the optical. This has a corresponding effect of heating the atmosphere, which shows up in its temperature pressure profile and would show up in its emergent thermal emission spectrum as well. In this way, metallicity can be sort of constrained, and we'll hear more from Eileen about retrievals and how we use methods to actually infer atmospheric composition from spectra later in the week. Okay, so we talked about clouds in the Earth spectrum, and that last example for metallicity was a completely clear sky spectrum, but clouds are incredibly important, are seen everywhere in the solar system. All the solar system planets pretty much have clouds to some form or another, and you get clouds in a general sense when the pressure temperature profile, which are shown here in these colors, crosses the condensation curve for a given species. So here again, we're looking at, pressure on the y-axis, temperature on the x-axis. And so if we just, well, I'll leave that up. If we just take a look at the 550 Kelvin effective temperature pressure profile curves, we see that they cross the water condensation curve up here at low pressures or high altitudes. So we expect to see water clouds for these cooler planets high in the atmosphere and showing up as the sort of dominant species setting our cloud top in our thermal emission continuum or our reflected light spectrum. But for hotter planets, they don't cross like these condensation curves. For the more volatile species, water and other species will stay in gas phase, and instead we end up with more refractory clouds, these exotic clouds that we just don't have a reference for in the solar system, but we see are ubiquitous in brown dwarfs and giant planet atmospheres. So you end up with this picture of kind of layered clouds, depending on the temperatures of the planet, and of course, its gases that are present there and what can form clouds. So we saw with the reflected light spectrum for water clouds that you can constrain cloud compositions by taking a look at absorption features and use those to constrain the composition of clouds. But you can also identify indirectly the composition of clouds by this sort of context from the pressure and temperature profile and understanding what clouds you expect to be condensing at the pressures and temperatures you're probing in your emission spectrum. There is another way to constrain clouds as well, which includes reflected light phase curves. And this is an area that I'm really excited about in the future, being able to probe more with perhaps Roman and with the Habitable Worlds Observatory. So reflected light phase curves measure the disk integrated planet brightness as a function of phase. And so here we're looking at Jupiter phase curves for wavelengths spanning from 300 nanometers into the near infrared. And they're compared to this cosine and Lambertian curves, these sort of smooth curves that are kind of a simplified analytic form for how you can expect a planet, its brightness to change with phase, from full phase here when you're looking at the planet fully illuminated to crescent and new phases here where you get no flux reflected off the planet due to the geometry. But we see radical departures from Lambertian and cosine scattering for planets in the solar system due to scattering properties of the clouds. And so these optical phase curves provide a really awesome way to probe aerosol, Rayleigh, and even perhaps surface scattering properties of exoplanets and provide another line of evidence for recognizing clouds that hopefully we'll be able to take advantage of more in the future. All right. Moving right along, we're all right, going to start part 3 here, where I'll give a brief overview of past, present, and future results or future goals. Here, I'm going to take special note to call out the talks later in the week. I think we're going to be hearing in a lot more detail from experts in the field about sort of each of the things I cover in this section. So this will be pretty high level. So, and we heard a bit from Beth yesterday about sort of the initial photometry. Here, we're looking at a color magnitude diagram with magnitude here, brighter objects on the top, dimmer objects on the bottom, and J minus K color here. So redder on the right, bluer on the left. And in general, brown dwarfs start hot and cool over time, reddening until the LT transition where they move left here and become bluer. And so what we saw in the initial photometry was these high or lower surface gravity young planets were remaining red instead of sort of transitioning blue, likely due to their surface gravity and how it affects the ability to detect methane. And so the initial near-infrared spectrographs that were able to directly image these sort of same class of planets provided spectroscopy to sort of bolster these findings and help explain that we were not seeing methane in these spectra as sort of expected. Beth touched on this yesterday. And so it sort of verified that the low surface gravities from these planets had something to do with the reddening and the lack of methane in their atmospheres. So 51 Eridani b, of course, being much cooler, was this first strong methane detection and sort of suggests that this LT transition that we see in brown dwarfs happens at much cooler effective temperatures for lower surface gravity young planets. So this is, exciting beginning to being able to get data and constrain these young planets and put them in context with brown dwarfs. I want to take a minute to highlight really exciting possibilities and work that's been done to map the atmospheres of brown dwarfs and in the future exoplanets. So Doppler mapping can be used to infer the surface heterogeneity or map of a planet in emitted light or hopefully in the future reflected light. And you can do this when rotation periods are relatively short, such that you can have an observing campaign and watch a planet as it rotates, but also that you're looking at a bright enough object that you can have short enough exposures to actually capture sort of peaks and troughs in the time variability of a rotating object. And you also sort of can only detect this for planets that have heterogeneities in their emitting or photospheres. So this would be due to like patchy clouds, or on the Earth, we have continents and oceans and clouds that reflect light in very different ways, as we saw earlier. And this can lead to strong time-dependent variability should we ever be able to detect that. And so, it's exciting that the high resolution spectrographs on the ELTs will enable similar mapping techniques for directly image exoplanet companions to sort of build up crude maps of planets that we just can't spatially resolve in any other way. More recently, we're all really excited about JWST, and it's pushing the field forward. This is another figure Beth was showing yesterday with looking at the first ever detected direct detection of an exoplanet beyond 5 microns here. And so while this was generally consistent with past studies of this planet, it was really nice to see that verification of consistency with past data, but also it really bodes well. JWST is performing excellently for this. And so stay tuned for Kim's talk later in the week to dive deeper into ground versus space and JWST observations. But I think that this bodes well for being able to study these planets in more detail, young giant planets widely separated from their stars at sort of longer wavelengths than we've had access to before. Also, I just wanted to show this beautiful picture of the classic system HR 8799, where we see the beautiful family portrait of the planetary system here at short wavelengths, and we see the inner disk emerging at longer wavelengths, and we can directly see that here in the images. So if you like disks, definitely stick around for John's talk coming up next. And so we have Roman coming down the pike. And so here's my obligatory contrast curve plot. And we see that Roman is going to be the first space-based coronagraph capable of reflected light measurements of gas giants. And while it will be a technology demonstration, it's very exciting to see us pushing the contrast down to about 10 to the minus 8 flux contrast, and or perhaps better. And this is really promising. If the technology demo works out well, then I think we're in for a treat with reflected light studies of gas giants, and starting to understand some cloud properties and constraints on gas abundances for classes of planets that we don't currently have access to. Looking even more forward to the future, I'm really excited, as I hope you are as well, about the Habitable Worlds Observatory and its capability to search for life. And so the goal here, of course, is to obtain reflected light spectroscopy of an Earth-like planet or many Earth-like planets orbiting sun-like stars to perform a robust search for life beyond the solar system and in the solar neighborhood. And the challenge here, of course, is to push our contrast to 10 to the minus 10 to access the reflected light of Earth-like planets in the habitable zones of sun-like stars. And so this will also require tight inner working angle constraints, but it's great to see this path already underway, working our way down to lower and lower contrasts as we see, us getting closer to this goal. And it's nice to see this progress. And I think we have the roadmap here. And the cool thing about the goal of reflected light studies of Earth-like planets orbiting sun-like stars is that if you can do that, you can do tons of exoplanet atmospheric characterization of all the types of planets in between, and sort of fill in this parameter space between what Roman's capable of doing, what the ELTs are capable or will be capable of doing, so it won't just be Earth-like planets. Of course, that is the sort of top level like engineering setting goal, but we'll be able to do gas giants, Jupiter analogs, and sort of super Earths, mini Neptunes, and fill in this parameter space. But of course, the search for life is really intriguing and a huge motivator for myself, and I hope many of you out there. And so we do just have knowledge of life on Earth, and that seems like a data point of just one. But since since life has modified Earth's environment over time in several distinctive ways, we actually have a sort of a sample size from the geologic evidence from the rock record. We have evidence of Earth's atmosphere through geologic history. Of course, we want to be able to search for the modern Earth spectrum with our classic oxygen, ozone, methane biosignatures. But if we go into the past, when oxygen was less prevalent, we see that we can use the ozone feature to still detect really small quantities of oxygen when it had not built up to as large of amount of oxygen as in the current Earth's atmosphere. And looking even further back, we can see the prevalence of methane produced by methanogens, early metabolism developed by life in Earth's in the Earth system. And so by using this sort of Earth through time approach, we have multiple archetypes for life on our planet that we can use as a testable hypothesis to go out there and search for. So that we have more than just a n=1, we have a n=a few to recognize life on other planets. And we are excited to use the Habitable Worlds Observatory in the future to do this. And so, all right, with about 5 minutes left, I'm going to just put my summaries up here and say that we've taken a look at the reflected and thermal emitted light from planets and how it encodes fundamentals about the atmospheres that can then be decoded thanks to high contrast imaging, the universality of physics and chemistry, and lab measurements that help us fill in the pieces using knowledge on common and uncommon gases. The strength of diagnostic absorption features depends on tons of factors, including the observing technique, what wavelengths we're looking at, the nature of the planet and the atmosphere itself, including the composition, metallicity, the presence of clouds, and the altitudes that those are at, the thermal structure, the surface properties. There's so much rich detail. And that's a challenge when it comes to predicting planets we don't know that much about, but there's also the opportunity to learn so much about planetary atmospheres by making these observations, by building the instruments that allow us to fill in this parameter space and sort of do comparative planetology for a large number of planets. And while our current direct imaging measurements are capable of probing young giant planets and have really placed them in context with field brown dwarfs and have done amazing work, we'll hear a lot more about that later in the week, with Roman next and HWO coming down the pike, well, in a couple decades, then the path is sort of set, the roadmap is there to expand our atmospheric studies across a broad range of exoplanet demographics and perform a robust search for life in the future. So I thank you for your attention and be happy to take any questions. Thanks.
Awesome. We have time for some questions. Yes.
Thank you for the lecture. I'm Ekrem from Washington University. I wonder what could be the effect of planetary rings and exomoons to the reflected light spectra?
Yeah, so the question is about the effect of planetary rings and exomoons on a reflected light spectrum. This is something that that hasn't been studied too much. I think, given that rings and moons would be unresolved, they are a potential confusion source. Marianne Limbach had a recent paper about how you can have moons occult the planet's disk, and even though just like a transit of a planet orbiting a star, and that could sort of cause a time variability or impact the observed spectrum. And so I think it's an area that is worth looking into. In general, what are the astrophysical sources of confusion that will make it more challenging to infer sort of accurate, unbiased stuff about exoplanet atmospheres. So yeah, thank you for that question.
Thank you.
Okay, well, thank you for your excellent talk. My question is about a 3D model. So how can you estimate the rotation period? If you follow a certain species, is it possible only the species rotate very fast, embedded in a fast wind? How can you confirm it is the planet rotate very in this speed? Thank you.
Sorry, it was hard to hear you through the mask. I heard 3D models, which I didn't talk anything about.
Yeah. I mean, the rotation period.
Yes.
Yeah. If you follow a certain species, how can you confirm the whole planet move or the certain species move very fast?
Okay, so how do you sort of distinguish between sort of 3D effects due to rotation versus sort of like dynamic weather
Yes,
that would sort of cause variability? Yeah, that's a
Yes.
great question and something that is a challenge. So I think with rotation, you want to look for sort of a quasi-periodic or strictly periodic signal that is sort of locked into something like a 24-hour period, whereas dynamics kind of have a variety of timescales, and so you might see variability. But I think we can look to the study of stars and brown dwarfs, which similarly have these types of complicating effects when studying time variability. And so it's actually, I think, an opportunity to learn about those 3D effects, whether it's constraining the rotation period or constraining the sort of dynamic timescale of variability on a planet.
Okay, thank you so much.
All right, we still have time for a couple questions. I'm wondering, do we have any questions online? No. Okay, but I see a question over here. So coming with the microphone.
Hi, Marvin Jikji, Arizona State University. Thanks for the great talk. So some of us may have gotten the email yesterday saying there's going to be the director's discretionary time searching for atmospheres around rocky planets around M dwarfs. So I think a lot of us are still maybe feeling pessimistic about the prospect of that. So I guess my question is, how do we really tell whether something is atmosphere-less or whether there's just so many clouds that we can't detect any of the speed? Like, is there really a way to determine the difference between spectra of those two different types of planets and atmospheres?
Yeah, that's such a good question. And it does relate to sort of this population of small, hot, or warm, rocky exoplanets that can be studied with JWST because they transit. And so it's not, in the direct imaging context, I think it's super important to try to use JWST where it excels and try to understand the prevalence of atmospheres for rocky planets around M dwarfs, because I think this is something that definitely the ELTs will have an opportunity by studying M dwarfs to think about as well. But when it comes to HWO, and it's just harder to make direct imaging measurements of these really close-in planets, especially in M dwarf systems where they're really tightly packed. So on the one hand, it may be discouraging that rocky planets around M dwarfs, just maybe they don't have atmospheres, but I sure would want to know that from coming out of JWST, going into, say, search for life with the Habitable Worlds Observatory, so we know, okay, should we be looking more at K dwarfs and G dwarfs? And I think that is the beautiful path of direct imaging, is to open up that search to a broader range of planetary types. Yeah, I think it's a really exciting time, and it's a great question. Thank you.
All right, so we have time for one more brief question.
Thank you so much for your really great talk. I can't remember if it was on your metallicity slide or your cloud slide, but somewhere some of your plots were a function, or the lines in your plots were a function of sedimentation efficiency, which is a concept I found really confusing. Can you briefly describe that FSED parameter? Is that possible?
Yeah, that is confusing. So yeah, in a most basic sense, it's quantifying the efficiency with which condensates settle gravitationally and sort of drop in altitude. And so it's tied into the surface gravity of the planet and the temperature that can affect sort of what altitude the clouds form at. And so that's why they kind of are important. And important there is that sedimentation efficiency is kind of changing your where your clouds are, in altitude where you end up with the thermal emission coming from. And so I think there's a lot more to say about it, and it is confusing, but I think I'll stop there. Thank you.
So let's thank Jacob one more time.